Should we go for it, Robin?
Yes, yeah, it's 8 o'clock. Am I introducing this?
I think so.
Oh, right.
Right, I'll just minimize that. Anyway.
Well, as everybody's joining, thank you very much for coming along, and thank you very much, Dr. Andy French, for running this session. Please don't feel that you must follow every detail of this as we go along. You're here to see the overview and the sorts of things that can be done. So they're presented to you as a nice sort of, uh, you know, set of dishes like at a dinner. It doesn't mean to say you have to know every detail about how you cook the things before you eat them. So get the overview, write down on paper things that interest you so you can follow them up. But don't sort of get bogged down in detail and ask little questions about some obscure thing that was on the screen 5 minutes earlier. So enjoy it and get some ideas out of it because there are plenty that are being presented this evening. Over to you, Dr. French.
Right, thank you very much. Good evening, everybody. Welcome back to the British Physics Olympiad Computational Physics Challenge. My name's Dr. French from Winchester College. We're going to be talking about gravity and astrophysics tonight. And well, it's about a sort of smorgasbord of ideas, but there's going to be a few things which are a kind of recipe in progress tonight. So you lucky people are going to experience, well, at least for me, is going to be a bit of research. So we'll be kind of following the pattern of the last few years in terms of gravity and astrophysics. But there's going to be some new stuff. So hold on to your hats. I will show you some links to some work in progress. All right. So let's just minimize this and I will show you where we're going to begin. Right. This was sort of the general course, but if I bring up my little website on the Eclecticon, I'll show you where a few things are. I believe it's been put in the chat. So what we've got, so I suppose there's three things actually. One, in terms of publications, we had an email from a student talking about numerical methods and Runge cutter and constant acceleration between time steps, which we've done in the course a few times. So I wrote a paper in 2019 with a colleague of mine, Dr. Klern, about numerical methods as an introduction to calculus. So you can have a look at that. And if your school has got access to physics education, you can access that paper from this particular page here on the Eclecticon. We're also going to be looking at some astrophysics. There's kind of two things, really. There's an amazing 3 blue, 1 brown video by the incredible Terence Tao, one of the world's best mathematicians, living mathematicians, in fact, as well. Under my notes on the cosmology page, so there's all sorts of stuff here. And I've got a new presentation called the Cosmic Distance Ladder. So this is my take on Terence Tao's video. There's a kind of, the idea of the distance ladder, as this sort of illustration possibly suggests. Let's go and have a picture of it, shall we? Which is this one here. Let's go for the first page. There you go. So the idea is that you sort of start with the radius of the Earth and how you measure that. And then you look on the next rung of the ladder is how far the moon is by looking at eclipses and other things. And then you look at the distance to the sun, and then by Kepler, the distance to the planets, etc., etc. So we're going to touch on maybe a few of these, maybe two, maybe something to do with Keplerian orbits. Actually, maybe three, something on the HR diagram, the Hertzsprung-Russell diagram. So this is our kind of rung number 7 or 8, looking at the distances to the nearest stars. And then from there, you can look at the distance to the galaxies. So basically, from a measurement on the Earth, sort of Alexandria to Syene, thousands of years ago, plus a few time measurements, it is in practice possible to go from the Earth all the way to the wider universe. So if you're interested in that, do watch the 3 blue 1 brown video, and you can download this sort of lecture set of notes. A lot of that's going to be going into Science by Simulation 3, which is a work in progress. But there's another project which I've been involved with over Christmas, which is looking at the interior structure of stars. So that is very much a work in progress. There might be some errors. Maybe you can find some. Where do we find that, you might ask? So that is going to be under this Structure and Evolution of Stars link. So if you click on that, so you get a PDF. And there's all sorts of stuff that you might find that's useful for sort of introductory cosmology. So here's a kind of diagram of the evolution of stars, and it goes into things like the modeling the temperature of the center of the sun, and how the density versus radii works and that kind of stuff. So we'll sort of dip into quite a few of these things. Right, so I think what we'll do is we'll actually start off with the Hertzsprung-Russell diagram. So I know a lot of you will have sort of looked at this before. And here you go. Here's one. Here's one I did earlier. Let me just make that nice and, oops, let me make that so you can see it all. So what we've got, what is the Hertzsprung-Russell diagram? Well, if you get lots of stars, and I found an Excel sheet, which I think is now available of the Eclecticon. I got this from, it's basically, I think, the mixture of the GLS catalogue from this website here. Yeah, it's all free, and it's about 50,000 stars. So I think it's really important, and it's very much in the spirit of this kind of course, that we don't just sort of look at an illustration and go, that's good. You want to kind of get stuck in with the data yourself. But getting data from stars, I always found is actually quite difficult. I mean, there's huge amounts of it. Gigabytes have been created every day. But I think there is a bit of a barrier to entry. Maybe someone from the astronomical community can sort of pull me up on this one. I wish they would, because I think this stuff should be really, really easily accessible. But to make it accessible to students, I think you need an Excel sheet, which you can then import into something like Python or MATLAB. So I found this one, which I think is great. So we've got 50,000 stars, and you get all sorts of information. The bits in green are the ones which I think I would like to sort of talk about. So what you've got is something called the effective temperature. So this is all about black body radiation. So of course, stars have nuclear fusion going on throughout their body. Most of it's happening in the core, but some of it will be happening sort of in other parts. So it's not like a flat plate that has a certain temperature, like that we use for black body radiation. So what you do is, if you relate the luminosity to temperature with your temperature to the fourth relationship called Stefan's law, you can use the luminosity to tell you what the temperature is. And so that will give you the temperature in Kelvin here. We've also got the luminosity in solar luminosities. So this star here is 184 solar luminosities. And then you can take some logs of these, and from the luminosity and the temperature, you can work out the solar radius. That's in solar radii. So this star here we mentioned is about just under 100 solar radii. It's rather bigger than our star. And if you plot the logarithm of the luminosity in solar luminosities and the effective temperature in solar effective temperatures, I think it's 5772 Kelvin, something like that, you get this amazing graph. So this looks a bit rubbish in Excel. So what I think the first thing we'll do is how we go from an Excel sheet with lots of data into something like MATLAB. And I always find that that's what you want to do, because this is a bit unwieldy, really. You want to better play with it, with speed and elegance. Stick it into another program. So this is, I'll show you how I made this picture. We'll start with there. As you can see, I've got a bespoke graph, and notice a slight weirdness with the Hertzsprung-Russell diagram, that you've got minus the log of log to the base 10 of my temperature, the effective temperature of my star, divided by my surface temperature.
Your graph, can we?
Sorry? Can you not see this, Robert?
No, we can now. Sorry.
Oh, fantastic. Right. Am I still? Is this all coming across all right? Okay, fantastic. Okay, so what I've got is, if you've got this sort of band here, and this is called the main sequence. So when stars of sort of like stars of fusion start to happen, they've collected from protostars, they've got hot enough in their cores, and then you still might have hydrogen fusion. If it's really hot, you might get amazing triple alpha, which is actually a 3-body problem, 3 helium nuclei coming together, and more exotic fusions at high temperatures. And what happens is you find these lie on this kind of diagonal line with some outliers, of course. This is the main sequence. And what we're going to try and do, I've made a sort of empirical black line on this. And if you can do some fitting, what that means is, if you know the luminosity, you can find the effective temperature for a main sequence star. And we can actually find the luminosity from the mass of the star. So in fact, all you really need to find out what's happening in a main sequence is the mass of the star. Obviously, a bit more detail, you need things like the composition, we call it metallicity. But essentially, all this is driven by the mass. Now you may say, well, hang on a minute, what about this big bulge here? What's going on? Well, that's the red giant branch. So as long as you may know that eventually, after 10 billion years, which is how long our star will last, blue stars last a bit less, red dwarfs last a bit more. Once fusion has kind of been exhausted, the star will swell up into a kind of dynamic phase. And then depending on the mass, it will either sort of like end up a supernova, or the envelope will disappear and you'll get a white dwarf, which are these ones down here, not very luminous at all. So there we go. We can kind of understand in one picture all the kind of possibilities that you get with stars. And the ones right at the top are the supergiants. So they're a bit different from all of these ones. So let's just look at a couple of things. So one, how can we deal with an Excel sheet, stick it into MATLAB or there or Python and plot this graph? So I'm going to give you some ideas. I say you'll be able to download this software from the Eclecticon. So what as we sort of talked about earlier, as Robin said, write down a few sort of sentences of what I've done, and then you can use that as a recipe for doing some Python. I think that's probably what I'd make a little mind map of this. So let's go and have a look. So I've got, this is the HR diagram, a bit of code. So what I've got is I've got two functions here, get star data and make HR diagram. Why have I got two? Well, basically the ingesting of the Excel sheet usually takes a little while. And what I'm going to do is I'm going to produce something called stardata.mat. And this is a data file. You can see it loaded up almost instantaneously. And in stars, what I've got are several fields. So stars.id, I've got something with 45,346 elements in it. So it means I can plot something. So let's just, I don't know, let's just go and plot one of those from the data file. So if I go and bring that up here, where's my command window? There you go. So if I go for plots, say, I don't know, let's plot, let's go for temperature versus luminosity, for example. So plot T_K versus luminosity L. I've got to use my stars as well, I think, for this one. There we go. L by L sun. All right, so there we go. And that needs to be on my fields. So I think what we'll do, I think this will work, I hope. So stars dot. So stars dot this and stars dot that. That should give you these ones. There we go. Brilliant. All right. So not particularly exciting graph, but the idea that we've got temperature here and we've got our luminosity. So that's hard to tell any sort of major relationship because, of course, in our HR diagram, that's all over the place. But we can easily make plots based on this data very, very quickly. So let's look at something that's a bit more interesting than that. But the point I want to make is that we want to ingest our Excel sheet. So how do I do this? This bit of code here, I use the XLS read function, and that gives me various arrays. So let's just step through this and I'll show you what happens. Oops, let's do that. So there we go. You can see it's taken a little bit of time to load up the Excel sheet. Actually, it's even going to let, there we go, got there in the end. So you don't want to be doing that every time. That would be really tedious. Whereas once you've saved a data file, that will load almost instantaneously. And if you're trying to sort of debug something, you want it to be slick. So what I'm doing is I'm going through the data and I'm turning arrays into something I want. So if I hover over this, I've got 45,346 elements by 19. That's a big spreadsheet. And I'm pulling out the ID, the declination, the magnitude, all sorts of things. And what I'm going to do is I'm actually going to work a few things out. So there's something called a color index. And what we really want to do is actually have the temperature in Kelvin that corresponds to. So you'll find this a lot when you're looking at data sets, that what you really want is something like temperature and luminosity, but that's not what they provide. So you've got to do some sort of mathematical transform. So this is called Ballesteros' formula, which I looked up. And so it's got this thing B minus V, and you multiply these by a few numbers, and that's a factor of 4,600 Kelvin. There's also something similar, which the absolute bolometric magnitude, and that can be turned into luminosity by this relationship. So there we go. So you've got all sorts of things which take the data and then convert it into a form that you're interested in. And I'm also figuring out a color that I'm going to plot for each star. It won't be the real color, but I'm using a sort of color map for this. So if you go back to our little picture, there you go. So in MATLAB, there's a kind of color map which goes from red to blue. So I've roughly mapped the temperatures onto that scale. So I think that gives you a nice sort of representation of what's going on. There we go. So the point of it is that you want to have control about what you plot and what you process. So you're making an ingester. So that's what that does. And then once you've got that, we can make a program which then plots something. And I'll give you a sense of how quick that is. So if I just run this, hopefully that will be nice and quick. So we get a graph of luminosities, and then we get some plots. And there we go. The coloured one appeared almost instantaneously. And I've plotted 50,000 points here. So let's just have a little look at maybe one of those things. This is a really nice thing to do. So this is the luminosity versus mass. It turns out there's lots of stars which are in binary systems. And so if you look at binary systems very carefully, what you can actually do is work out the mass of one of those stars. And so rather than trying to guess the mass of one of your main sequence stars, you can actually work it out. And then if you use a telescope to work out the power per unit area coming from it, and you can use something like parallax to work out how far away it is, you can work out how much power that star produces. We call that the luminosity. So if you plot them against each other, you get a nice empirical graph. And so it's pretty much goes as m cubed. So if we have, say, a sun which is twice as luminous as ours, that's going to be about twice the mass of ours. That will be about 8 times the luminosity, all right, 2 cubed. And this empirical graph that I fitted has a constant of about 5.78. So mostly this is both sides of my equation are dimensionless, because I've got a ratio of luminosities and a ratio of masses. That's the dashed line I'm plotting there. What I've done is a line of best fit of the curvy line, which is actually a sort of a semi-empirical thing based on different regimes from these binary stars. So you can work out the solid curve to be more precise, but actually for a lot of analysis of astrophysics, you want the just one relationship. So in other words, if you have the mass of a star, you cube it, multiplied by 5.78, you get the luminosity in solar luminosities, and then from your HR diagram, you can then work out all sorts of other stuff. So as long as it's a main sequence star, you can work out its temperature, all those other things. So that's pretty cool, isn't it? So there we go. So I think that's all I'm going to talk about that. But the idea is for trying to actually take quite a large data set. And I suppose 50,000 stars isn't really that large, but for the sort of purposes of education, kind of where we're at the moment, everybody, this is something that I think will be a good starting point. If you plotted a graph with 50,000 data points, I think that's going to give you some bragging rights. And if you can do that, then maybe you've got the skills to deal with something much bigger or a much higher data rate, which of course is what a lot of modern science is doing, where our telescopes are scanning the sky constantly, where we've got details of billions of stars now. So it all begins here. Okay, so before we sort of look at something more dynamic, any questions about data ingest, HR diagrams and that kind of thing?
Can you just share if people can find this exact Excel spreadsheet, the data set somewhere?
Right. Okay, I will do my best. Let me just see if I've actually uploaded it yet. If not, I will do my best to do that straight after the lecture course. Let's go and have a little look. It's on my website. So there we go. What I'll do, let's just don't save that one. So if I just minimize this, bear with me, lots of icons. Where do I put it? Here. Right, so structural evolution of stars. What I'll do, you can see these little MATLAB icons. I will make a MATLAB icon which will go just there. So if you can give me an hour and log on to this website, you will be able to download all the code which will go there. How about that? See, this is dynamic. Right, so let's go and have a little look at a few other bits and bobs. So let's go and have a little look at the sort of the course itself. So normally I start off looking at Kepler's laws. All right. So here we go. So here's Johannes Kepler with his enormous ruff, which kind of looks like it's orbiting his neck. I think that's quite nicely ironic. And here's a model of the solar system. You think, well, this is a bit weird because I've plotted Pluto. And the reason it looks quite strange is that actually Pluto's orbit is tilted from the plane of the ecliptic. So at various points, it may look like it's very close to Neptune, but it's just it's on a different plane. And also you might notice these orbits aren't that circular, because in general, this is Kepler's first law, that the orbits of the planets about a star, or in fact the orbits of any two-body gravitational system, is an ellipse. So here's a nice sort of diagram, which incidentally is created in MATLAB. Almost all the figures are here. So if you can sort of follow my mouse at the moment, let's just say we've got a sun here at the focus of my ellipse. And let's just say our star's mass m is much, much bigger than the mass of the planet. So in other words, we can ignore the kind of mutual center of mass. The center of mass of the system is the center of the sun, just to keep it simple. But if that's not the case, they will orbit about each other. We call this the barycenter. But that will also be an ellipse, but let's just not make things too complicated. Let's assume we've got a planet go around a star. So there we go. This is our ellipse. And there's some nice terminology with this. The sort of long axis is called the semi-major axis, 2a, and the semi-minor axis is the vertical one. Both of those numbers will define an ellipse. Now, you could do this in Cartesians, but perhaps more fun is to define it in polar coordinates. So if you've never plotted an ellipse before, this is quite a fun thing to do. So, and this is it. This is the equation. It's A, our semi-major axis, times 1 minus the eccentricity. The eccentricity is related to B and A by this sort of formula here. And what's downstairs is something that involves the cosine of the angle. So if B equals A, the eccentricity is 0, and that's a circle. And it's basically R equals A. But if epsilon tends towards 1, we get an even more elliptical sort of thing, object. And then a lot of you may know that Kepler's third law relates the period, so how long it takes to go around this ellipse, with the semi-major axis. So p squared goes as a cubed. It's one of the great results of pre-Newton, and of course Newton's law of gravitation, this inverse square law. If you combine that with some circular motion, you end up deriving Kepler's third law. So that's a kind of classic thing to do for A-level physics, or just a classic thing for any of you guys to do. So I'll leave that as a little exercise. You've never done that before. So we're going to kind of assume some of this information, and I'll give you some ideas of things that you can plot. Now, a lot of this stuff was part of the Computational Physics Challenge, I think was the second one. So if I just go show you where that is. So our main kind of website for this one, I go to physics courses, this one here. This is also in the chat. The challenges, we've now had 4 years. So this will be the 5th year, 2023, I think. He says, I think is solar system orbits. There you go, solar system orbits. So you can download that and you've got everything there. So there we go. If we go back to our little presentation, where is it? It's this one here. Right. So let's just say, what can we do with orbital things? Well, I'll just move that out of the way. I was going to skip across these for a little moment. Well, the first thing you might want to do is just plot the solar system, which is quite nice. And I think maybe we'll give that a go. Let's have a little look for, there we go. So yeah, so we can sort of plot these things. And so I'll show you a little bit of MATLAB code for doing this plot. And so there's some rather interesting things you can do. So I'm going to jump into, I've got lots of code fragments for this, but I think here's a sort of simple one. Where is it? It is orbits quick demo. That sounds right. So if I just load this up, right. So let's make this as big as possible. You can see what's going on. Right. So what we've got. I don't know if I can make this. Is this big enough to read, everybody? Or do I need to make it larger?
It's all right. Maybe just slightly larger.
Let's have a look. Can I do that? Editor view. Actually, can I do this easily? It's not in this section. Oh yeah, preferences. There we go. Let's go for fonts. Let's hope we can make that a bit bigger. Right. So let's go for something like 18 and 18 there. Apply. There you go. Look at that. Perfect. So what we're going to do is we'll have Earth and Mars, and we'll assume we've got circular orbits. All right. So what we've got is the radius of the Earth in astronomical units. So we're going to assume that's 1. And Mars is a bit bigger, about 1.5. And then we've got the period of the Earth in years. So orbital astronomical units and years are going to be our distance and time units. All right. So if we use Kepler 3, so the square on the period goes as the cube of the radius, then the period is going to be the orbital radius to the power of 3/2 or 1.5. So therefore, we can work out the period of the Martian orbit just from these bits of information. And then what I'm going to do is I'm going to work out a time array, all right, because I'm going to plot this for a certain number of years. So given the period of Mars is the bigger one, let's go for, say, 30 Martian periods. Actually, I think I'm going to go for slightly less. You'll see why in a minute. Let's go for 5 Martian periods. So I save that. And so this in MATLAB is a linearly spaced array. So this is your first time on this course. Linspace is a way we can construct a vector, a kind of spreadsheet of numbers. So linspace 0 to, let's go for 1 in 10 steps. And if I make it sort of a sort of 10 by 1 array, that's what this, the dot dash means a transpose. So if I ignore that, you've got columns. Perhaps a bit easier to see if I do it this way. So we basically 0 to 1 in 10 steps, and that's how we can construct our array. That's a really useful thing to do, because once you've got this, you could say, I don't know, y equals t squared. The dot means I square root each one. Whoops, not t, ans, there we are. And I could do, I don't know, I can plot y versus my 0 to 1 thing. So I could go for plots, and I could go for my linspace 0 to 1 in 10 steps versus y, and that should give me a nice curve. All right. So it's really easy to kind of create data and plot it in MATLAB. So what am I doing? I've got a time array. And what I'm going to do is I'm going to create some vectors of the angles. So this is the Earth one. So I've got 2 pi. And I'm going to, that's interesting. I put some random numbers in this one. I don't know why. Oh, yes, there we are. So I've got a random starting phase. So 2 pi times rand is going to be some fraction between 0 and 1 of 2 pi radians, which is a random number. So in other words, I don't always start in the same place. And then as time progresses, 2 pi times t over the period is how many 2 pi radians I run around. So every time I have an Earth period, I go all the way around the circle. Now I'm going to do the same for Mars, and obviously that has a different period, so it's going to take, it's not going to have such a large angle with time, and you can kind of see that the speeds of the orbits must be slower as you go out. The periods are longer here for the same angles. Then what I'm going to do is I'm going to use sort of r cos theta and r sine theta to work out the x and y coordinates for both Earth and Mars. All right. And then I'm going to plot it. So let's just go and do that. So here's my plotting. I've got plotting Earth and which is in blue, and Mars in red. And the other thing is just sort of set the size of the graph. So let's go and do that. And I'll put a breakpoint here. Let's just get back to my editor. And hopefully we should get this. So there we are. So here's the Earth and here's Mars. And you can see the relative orbits, and they're nice and circular. And if I run it again, you should find they are in a different place because of my random starting condition. I think I'll need to quit that and then run it again. And I should get 2 graphs now, I hope. Oh, no, I haven't. It's overlaid the same one. So there we are. But you can see it's plotting in a random place. So let's get rid of that. Right, so what the first thing next you might want to do once you've got your orbits is you might want to animate it. So this is how I do an animation. I'm just going to highlight this. So what I'm going to do is something very simple. I've got a stopping criteria. So let's have stop is 0. And I'm going to have to do a sort of manual system. You could do all sorts of key press functions and all sorts, but I'm just going to sort of set this to be 0. And what I'm going to do is I'm going to step through my arrays, my orbits. So I'm going to increment a counter by 1. And as long as that counter hasn't exceeded the length of my array, so this is my time array, I'm going to sort of update the X and Y position. So when my big star, which is where the planets were, I'm going to update those. So P Earth and P Mars, what are those? Well, these are my plots. So I've got the first 2 are my orbits, and then these guys are little stars, a red and a blue one. So let's just run that to that breakpoint. So there we go. There's the Martian one, and there's the Earth one. So I plotted these coordinates. There's 1,000 of them, and I plotted another set of coordinates, which are the Earth and Mars at some given point in time. Right, so if we then sort of march through this, what I'm going to do is I'm just going to update it and a little pause. So if I run that to here, Let's give that, let's quit debugging and run. There you go. I've set it to be quite slow, but you can see that the Earth is going rather faster than Mars is. Okay, maybe I'll set my time delay to be a little bit shorter. Let's go from 0.05 seconds. And that should be a bit more smooth. There you go. How's that? I hope that's all right. So there we are. So you'll end up having more Earth orbits than Mars does, all right? Because the period is related by Kepler's law. Okay, so there we go. That's a nice little animation. And the next you might think, well, what happens if we connect a line between these two things? What would that look like? Well, that's really interesting, isn't it? You can see the Mars sort of going behind the Earth here, this sort of retrograde motion. So what we can then do, I'm just going to sort of get rid of all the error parts here. How are we doing for time? Is I might sort of step through the orbital times and then draw a line between the positions. So let's set stop equals 1. So this part of the code doesn't happen. So this is never, this while loop never occurs. And all I'm going to do is I'm going to step through the times. I'm just going to draw a line between all the positions, and we'll see what that looks like. So if I just put a breakpoint here, there you go. And we look like something that looks like a horrible dark mess. But if I zoom in, look at this. So by plotting a line at how many points have I done here? So literally, however many data points, what have I got? I've got 1,000 data points over 5 Martian years. Okay, so and what we're doing is we're drawing a line between the positions of the Earth and the Mars. And we get this really beautiful pattern, but it's slightly asymmetric, of course. And maybe if we do a few more, we can sort of see maybe sort of more of those petals. So if I go from, say, not 5, but maybe 20 Martian periods, let's see what that looks like. There we go. So there we are. So a bit more, so this is starting to fill it in now. And if you do that for some of the other planets, particularly Saturn and Jupiter, you get some very beautiful pictures. So I'll, now you've kind of got the idea. But there's one more I might show you, is that what happens if we plot the orbit of Mars from the perspective of the Earth? So this won't be circles anymore. And the way I do this is really simple. Because we have an array of the Earth and Mars positions at any given time, that's how I've set it up here, right? So we've defined time, we've worked out the angles for Earth and Mars, we've worked out the XY coordinates. We can literally take one from the other. They're evaluated at the same times. And that's a bit harder if there are elliptical orbits, because you have to work out what the angle is versus time. That involves actually something called an elliptical integral. It's not something you can just write down. However, it is doable, but we're assuming circular orbits, so everything's fine. And if we plot that, we get something rather interesting. So if I run the whole thing, you'll see. So there we go. That is the orbit of Mars from the Earth. So this sort of retrograde spirally motion that might have inspired Ptolemy is no surprise if we view everything from the Earth's perspective. So the Ptolemaic view is perfectly valid, except it just makes things rather complicated. So hope you got the idea of sort of things you could have a go at by plotting these circular orbits versus time. And for inspiration, these are the kind of things you might get. So if I find the right slide for this one, there you go. So this was one of the tasks. There you can see it's in the yellow box. So the computational challenge this year will have something that looks a bit like this. And you get these challenges in these rather garish yellow boxes. So this was challenge number 6 in a few years ago. And this is Venus Earth. So Venus is the yellow trace and Earth is the blue trace. And you see a beautiful kind of 5-petaled star, all right, which is, well, to do with the ratios of the orbits. There'll be a kind of factor of 5. I think it's in 3:2, actually. It's a 5th. So there are links, you know, in the past, people thought there was a link between the orbits and musical harmony. If you do Jupiter Saturn, you get almost like a 3 ratio, okay? There you go. And here's Mercury Earth. It looks like some density you see under a microscope. That's Uranus Neptune. That's very interesting. And Neptune Pluto and Venus Mars. I quite like that one, actually. So there we go. I mean, yeah, they get a sort of cardioid shape for Neptune Pluto. And of course, that's a bit off center because Pluto is not in the plane of the ecliptic. I've got a picture of that, so just bear with me. Here we go. Yeah, so if you plot the orbits of the planets in 3D, you can see Pluto is not in the same plane. Right, so there we go. That's a sort of spirography kind of thing. Let's have a look at this one. So this is if you set a different planet being the center. This is Claudius Ptolemy, 100 to 170 AD. And as you can see from the picture there, the Earth is at the center of the universe. Well, obviously, we're taught in school that this is a nonsense idea, and it's far better to have the sun as the center of our solar system. And then, well, that's not really a good model either. Maybe this Milky Way, or maybe nothing is the center. But of course, it doesn't matter. We can put our coordinate system anywhere we like. So if you put it here, for example, this is what the inner solar system looks like. What I've done is I've overlaid Venus, Mars, and indeed the Sun. You can look carefully, you'll see the only circle here is the progression of the Sun based on where the Earth is, and all the other planets as well. This is relative to Saturn for the outer planets, and you can see Jupiter's got a really interesting pattern, a very sort of simple sort of 3-point, almost like a kind of Celtic pattern based on where Saturn is. The others not so more of a spirograph. Here we go, and I've just created a few others. You could put this on a T-shirt, maybe, and make some money from a young enterprise. Anyway, so that's that one. Anyone any questions, by the way, before we move on to something else?
Yeah, we're going through them.
Excellent. Right. So, okay. So if we kind of maybe go back to our, actually, I think I will show a few more because I've got, this leads on, this is in the original presentation. So I can show a bit more. So there we go. This is Mars. This is relative to Jupiter. I've got like this one. This is the Jupiter system for the outer planets. Right. So that's quite a nice one. So where you might want to go with this is that rather than everything we've seen so far has been the sun and a planet going around it. Okay, a sort of two-body problem. What happens if we introduce a third one? And we add the answer is we can get some amazing complexities. So what I've got here is two stars, and they're in a mutually elliptical orbit, the red one and the blue one. All right. So their motion is well known. And what I'm introducing is like a little planet here, which feels the gravitational tug to not just this one, but that one too. And it's in certain situations, its orbit is really complicated. So I'll show you how that works dynamically by running a simulation of it. So if I go for, which one is it? To figure out which one this is now. I think it might be this one. So binary stars and a planet, that looks about right, doesn't it? Yeah, here we go. Right, so let's go and run this. Let's get rid of the previous one. All right, so I'll see if I can sort of like, if I run this and show you the kind of computational guts of it. Well, what have we got? So we've got the masses of the stars are in a 3:2 ratio. I've got, let's go for a circular orbit. So this is a multiplier, which means if K is a bit bigger than 1, we'll get more of an elliptical orbit between the planets. And then I've got my planet's initial circuit is initially set on a circular orbit about star 1. There we go. That's the semi-major axis. So let's give that one a go like that. So yeah, so this would be, yeah. So my sort of initial orbit is a roughly 1 astronomical unit from star 1. So if I run that, hopefully, there you go. And you'll see it's quite pretty, doesn't it? So what we've got, these are 2 in circular orbits. One's bigger than the other. And my planet, which is initially orbiting about star 1, is sort of feels the tug of this one. And it's a stable system, this one. All right, but it forms what looks a bit like, if you've seen the film Dune, one of the sort of sandworms. I think if you look carefully in the center of the screen, that might give you nightmares. But that's sort of, this is what this little planet does. So we can make this quite unstable by moving it to maybe a different location. So let's try and maybe make, let's maybe change the masses. So let's have star 1 being a bit bigger, like 5 solar mass. Let's see what happens there. There we are. So that's even more stable. So perhaps we can make it a bit less stable. But let's go for a bigger. Let's make that maybe make that let's go for, I don't know, 0.8 times the orbit of the second one. Let's see what happens. Oh dear. That's not stable at all. I think you seem to have hit one of the stars. That's bad. Right. So you can really have a good play with this to sort of see if you can find out interesting systems. Yeah, that's not stable either. There you go. So yeah, so it does a few orbits and then it gets too close to one of them. So let's try one of these. So I'm making the orbit of star one a bit smaller. Yeah, that's still unstable. Let's go for 0.4, I think. No, that's not too bad. So it will orbit a little bit and then eventually becomes unstable. And so if any of you have read the Three Body Problem book, it became a Netflix series. I mean, obviously that had 3 stars, not just 2. But I think the idea is that this sort of star would be sort of thrown out and then get close to the 2 stars. So, you know, the population of 3 body gets sort of frozen and then burnt. But eventually, this might happen. And it gets too close to one of the stars and ejected from the system, or perhaps absorbed into one of the stars. So obviously that would be a disaster for the planet of 3 body. So remember, this is really interesting stuff. So that a 2-body system interacting gravitationally you can solve. Throw in another planet and you cannot analytically, as far as we're aware. So you have to do numerical method. So what is that numerical method? Just in rough handfuls. I think I might have a little slide on this. Just double check. Yes, I do. Good. So what we do is use something called the Verlet method. So let's just walk through this very simply. So what you're doing is you're assuming constant acceleration motion between time steps. And we've seen this, if you come to the previous talks, you'll see this again and again and again. So ut plus a half at squared, v plus at is how we update the velocity. There's a little slight wrinkle here that we do a sort of assume a kind of constant acceleration to work out the velocity. And then what I do, because acceleration may actually depend on velocity, I do this little extra update and then average it. So you'll find that makes the method a little bit more accurate. So it's I call this the velocity-dependent Verlet method. But you could probably omit that step with a small time step and you probably will still work. But the point is that you've got constant acceleration motion between small time steps. And that means if your acceleration can vary, and why is this in a bold font? Because this means a vector quantity. All right, I think I've got a little picture. Yeah, I think we can probably go with this. So if you imagine what is my vector in this case? So let's deconstruct this thing in the red box. What we've got, here's my coordinate system, and here are my 2 masses. So I've got 2 masses here, and R1 is the vector of this mass, R2 is the vector of this mass, and R3 is the vector to my little one here. All right. So in particular, I'm in this book, I'm ignoring the effect of gravity between all 3 bodies. This one just feels that one and that one. But in principle, you could have as many bodies as you like. And so what we're doing is we use Newton's law of gravitation to figure out the acceleration component resulting from the force of 2 of these. So for example, if I want to say, okay, what's my gravitational force of this one and this one together? Well, what I need to do is work out the distance between them. So I go down that vector and up that vector. So the difference between those 2 things. All right. And then I take the magnitude of it. So there we are. There's Newton's law of gravity. Why is it a cube, not a square? Well, I want the direction of my acceleration. So that makes sense to actually use this vector distance here. So I've used I and J rather than M and M, but so I can sort of go down J and up I to have the distance between these 2, the vector which points between these 2 masses. So you can code that up in something like MATLAB, maybe in X, Y, and Z in separate parts, and you can work out the acceleration between these 2 objects. And then what you do is once you've got your acceleration, you can work out what happens next with your Verlet method. And you can make some really crazy stuff. So here we go. So that's what we're doing. Now, what happens if we had lots more objects? So I think it's this one. So I've got a few things now where I've got lots of objects. So if I go back to MATLAB, it's pretty easy if I do this dynamically. So let's go for do I have the ring one? Starter white dwarf, I think I call this. So there we go. So if I run this, what you can see, if I shrink this down a little bit. There you go. Right, so what we've got is a whole bunch of circular orbits. So quite several thousand masses orbiting in a circular sense in concentric rings. And I've got this other little planet which is going around. Now, what happens is, once it completes an orbit, we're assuming lots of mass is now ejected. Bosh, like that. So what happens now is that the mass of the central star is now changed. And so what it means is that the little planet here is now on an elliptical orbit. That's quite a nice little math problem to solve, is that what happens if the mass changes drastically. Obviously, if you had a sort of supernova, it might, knock this thing out of the system. But let's assume maybe it produces lots of neutrinos instead. So a sort of neutrino explosion. And of course, my original orbits now don't quite work because I don't have the same gravitational force anymore. So that's quite a nice little simulation. And I think probably the most impressive, though, is the interacting galaxies, which when I was at university, this was one of the projects we were set. So, so what I've got here are two stars, or two galactic centers, in mutular circular orbits. One of them is a mass 5 and one of them is mass 3. So this could be solar masses, could be galactic masses. But initially I had circular orbits, but of course these little masslets feel the gravitational force of these two. And you end up getting these amazing sort of tidal tails that are formed. I think the structures are quite beautiful, actually. And depending on the ratio of the masses, you can get sort of quite significant transfer between them. So let's go and run this with a bigger ratio. So if I go for let's go for 15, shall we? Right, here we are. So there we go. So now this one really is devouring this galaxy. So I've set it so if the masses get a bit too close, they kind of bounce off. So you have to sort of realize this is a numerical simulation. So when the masslets get too close to the stars, obviously gravity could cause an infinite acceleration. So you have to sort of hard code that. So this one's going in a little orbit, this one's going in a big orbit, and you've got these sort of tidal tails. And we kind of see these structures if we look out into the sky. So perhaps these simple simulations can actually yield something that give us some insight. Remember, this is actually running in real time over the internet as well. So I've not pre-computed this at all. This isn't a supercomputer. This is just my little sort of desktop. So very easy, very doable. Anyway, I think that's quite pretty. Right. So let's go back to the presentation, and we're nearly finished. So I'll do a few more, and then we'll take some questions. So there we go. The interacting galaxies we've just seen, tidal tails. There we are. There's some screenshots of my kind of progression here. So I've got starting off with mutually circular orbits, and then we'll sort of see what happens in the general case. And after not a long time, you get something that looks a bit like this. So that's the Messier 83 galaxy, and you can see these sort of spiral arms. So where do they come from? Well, they come from this kind of thing. So there we go. I think this is a simulator just with 52 masses randomly assigned, and this is what they produce. And there we go. Sort of random filaments. Maybe on the greatest scales, maybe this might explain what's going on. But you do see some really complicated motions at the center of galaxies. So, for example, this is Sagittarius A star, which is a supermassive black hole, probably billions of solar masses, right at the center of the Milky Way. Most galaxies, we think, have a black hole right in the middle of them. So if you're really close to that, I say really close, we're still a long way away. These are in arc seconds. But the orbits of the nearby stars are highly elliptical. But nonetheless, they're not really interacting with each other. So each of these ellipses kind of implies that there is a two-body problem, the black hole and the star. But you see them, very, very highly elliptical. So, scientists have taken photographs essentially of the black hole in the center of our galaxy, and I think it's Andromeda. So a few years ago, and so we can certainly track the motions of these stars right at the centre. There we go. I think I might just end with this one, which is perhaps a bit closer to home. So you probably know that the Moon Earth system is not entirely point particle based. So although this is very much not to scale, we have tides on the Earth. The effect of the Moon and the Sun, the tug of bodies of water. But if you're on the Moon, in fact, Artemis, of course, is going to be going around the Moon in hopefully a month's time. You experience moonquakes. So the effect of gravity as a result of the Earth not being a point particle will change the gravitational force across the planet. And this bit of mass at the bottom, it's a bit complicated, but you can see a GM over R. There's a sort of there's a GM over R squared term, but there's also up to bits and bobs here where you can work out your gravity field. So I've got a little simulation of this, a rather extreme version. And what we're going to have is we're going to have a sort of a planet and a moon. And around this planet here, I've got a kind of circular orbiting water mass. Obviously, this is a very extreme version. And you'll see the gravitational tugs on that mass. So if I kind of run my simulation, but this is all the same stuff. I'm using the same ideas of a Verlet method working out my in-body problem. So it is, now where have I put it? I think it's under tides. There you go, tidal sim, I think it's this one. So yeah, there we go. Right, so here we go. So here's my huge planet, and you can see this sort of tidal bulge being drawn by this one and this one, and that will start to distort from its circular pattern, all right, by this mass here. There we go. So there we go. You can kind of see a model of tides as a result of this thing going around, creating this sort of tidal bulge which rolls around the planet. Obviously, that's on our scale, you could barely see this, but you kind of get the idea if you can take things to extremes. So there we go. What looks like a kind of complicated thing is not really that complicated because you're just scaling up the numbers. If you can work out a circular orbit and you can work out how acceleration works with the Verlet method, all you have to do is just put that in a loop with all the rest of your masses, and you can create something which, I think looks quite cool. So there we go. So we've looked at some orbits. We've looked at some data analysis, plotting from a HR diagram, and lots of fun things you can do with orbit calculations. So, depending on where you are with your programming, pick one of those. If you're really new, I just see if you can get a plot of circular orbit. But if you're, got a bit more skills, maybe try something like this with a sort of rings of masses to go around a loop, and then maybe a two-body system like this. So I hope that was fun. And any more questions? If I just go back to here. And I think we will stop there. Thank you very much, unless there's other questions.
There are a bunch of questions in the Q&A. Feel free to scroll through them and answer what you like.
Sure, yeah. Let's have a look. Can you re-explain the Verlet method, please? Of course, yeah. Can you use the Computational Request Award? Oh, I'm sure you probably can. Let's have a look. What do the green waves represent? I'm not sure what that quite means. Can the video be a voiceover? Right, so there's quite a few questions on the challenge itself. How much programming do we see? Why can't we use Rust and Run Cutter? Right, okay, so a couple of little things. Firstly, on the challenge itself. You can do it. You don't have to appear yourself in the challenge. In some ways, that might be a good idea for sort of, because we'd like to ask you to use the videos if they're very good ones. It'd be nice to put them on the BPhO website. So if you want to remain anonymous yourself visually, you don't have to be in the video. Obviously, if you want to be, you can, but it's the science and physics you really do the talking. So most videos we've seen so far is a kind of voiceover of what we've seen. So they'll show the answer to a problem, some code and animations like I'm doing today, and then they will have a voiceover. It's important if you're doing it as a pair that both of you kind of take it in turns. Okay. So what was the other one? So the Verlet method. So I think what we'll do is we'll go back to my presentation, and I'll show you what that looks like. So Verlet method, I think. So let's go for maybe this one. I think that's probably the simplest one here. There we go. So so Verlet method is constant acceleration motion. This is no different from what we did before for looking at kind of motion of projectiles and air resistance and that kind of thing. We're using constant acceleration motion between time steps. So ut plus a half at squared is the new displacement. And the only thing that's different from what we've seen before is that we're using vectors here, right? Because my acceleration may point somewhere else, it may not be in a straight line. So in this situation, the acceleration of two particles goes in the line that connects them. But because their initial velocity, that means they might be bent into a circle. They probably won't just come together. Our law of gravitation is a bit more complicated than certainly a constant acceleration, because it depends on the square of the distance between them. And indeed, the direction is the vector distance or the vector displacement between those two things. So there we go. I guess I've used a small wrinkle for this, is that I've updated the velocity. I then used the velocity to work out a kind of modified acceleration, because in general, acceleration might depend on the velocity itself. In terms of gravity, it doesn't, of course. But if you're using, say, air resistance or, I don't know, electromagnetism, your force and therefore your acceleration might actually depend on how fast your source particles are moving. So you might need this step. This step here is irrelevant for gravity because there is no velocity dependence on our vectors. Have I missed a question? I think that was, Runge-Kutta. So the Runge-Kutta method is a more advanced version of this. This goes as delta t squared, whereas Runge-Kutta, the simple one anyway, you can make it as complicated as you like, goes as delta t to the 4. It's a fourth order method. And you get, although there's a bit more computation per time step, you get a more precise calculation. So I explore that in the paper. If you want to know about Runge-Kutta, it's in Science by Simulation 1. It's also under here. So if you go to Maths, you go to Calculus, you go to Numeric Solvers of Differential Equations. Is it that one? I think it's that one. And yeah, here we go. So this is probably a bit small to put on a screen, but it takes you through it. And there's a variety of methods for working out solutions to an equation with a derivative in it. So this is the Runge-Kutta one, I think. There we are. So if I make that as big as possible. So what you do is that if you have some function, y of x, dy by dx is this, and you want to find out what y versus x is, you increment it by a little bit in x and y, and then you work out, you have to sort of back substitute these quantities into your function. And there are 4 of them, and you kind of add them up. And basically that gives you a method, which is the error scale is the 4th power of your kind of time step, or in this case, so delta x is your is a little bit, so you're incrementing this axis here, and you're working out what happens next. And you'll find, if I compare these things, so this is the Euler method where I'm just incrementing a little bit. So maybe if we compare like with like, I'm not sure I have actually. But this is my Runge-Kutta method. It's a much smoother solution to, in this case, dy by dx is sine of xy, which you can't really integrate. So there we go. If you want to have a go at something a bit more advanced, this might be how you might start. But all the simulations you've seen so far are using the Verlet method, so constant acceleration motion. Any more questions? In that case, I think it's nearly 9 o'clock. So thank you very much. We'll do something completely different next time. And between now and then, pick something from today and have a go, whether it's literally just plotting a circular ellipse or an n-body problem which you can optimize for speed. Who knows? Thank you very much, and see you next time. So